Hello everyone and welcome. Thanks for joining us for today's webinar, where we'll be taking a first look at the new features and improvements coming in the next major release of LimitState GEO. I'm Tom Pritchard and I'll be hosting the session. Our speaker for today is Professor Colin Smith, who is Director at LimitState and the originator of the Discontinuity Layout Optimisation, or DLO method, which is the powerful analysis technique that underpins LimitState GEO. In this webinar, Colin will walk you through some of the key enhancements and new capabilities that we're introducing into LimitState GEO version 4, with a focus on what they mean in practice and how they can add value to your day-to-day engineering work. The main presentation is going to run for about 25 minutes, and there will be 5 minutes or so at the end for your questions, which you're welcome to submit at any point using the Q&A panel in the interface. We do aim to cover as many questions as we can during the time available, but there sometimes isn't quite enough time to get through them, so apologies in advance if we're unable to get round to yours. We do follow up after the webinar with an email to answer any questions that are left outstanding. So without any delay now, I shall pass you over to Colin, who's going to take you through the new features and improvements in LimitState GEO 4.
Okay, well, thank you, Tom. For that introduction, I will just try and get this, there. So just as normal with our webinars, just to whet your appetite, for those of you not familiar with the software, we kick it off with a slide just showing you a selection of problems, types that can be solved by the LimitState GEO software. And hopefully, as you can see, the software has been designed to identify the critical collapse mechanism or ultimate limit state for any problem type in the form of a slipline mechanism. So that includes conventional geotechnical problems plus also reinforced soil type problems. So in terms of what I'm going to talk about today, essentially I'm pleased to give you this preview of the enhancements available in the forthcoming release of LimitState GEO version 4. Won't have time to cover them all. But we will take an overview and look at 3 core aspects of those enhancements. As some of the audience will be users familiar with software and some won't be, I'll try to cover some of the background of the software while demonstrating new features, and I'll use a few slides at the beginning and end for introduction and summary. And as Tom said, there should be time at the end for questions. So let's have a look at the enhancements. So to sort of give the overview, we've added more features. The software solution is more efficient, hopefully more informative, and we've included a number of customer requests into those additional features. So we're going to kick off looking at usability and efficiency. Most of our customers comment on the ease of use of the software, and we've aimed to maintain that while adding many new features. So we'll look at a few now that should further enhance the usability. Those listed on the slide here, but I will pick those up in the software just there. So let's just pull that up. So this is the kind of core interface to the software. We're going to click on New here, and you can either make a model or import it from a DXF, or we have a number of wizards that allow you to build standard problem types. We're going to work with a simple footing. So brings up a wizard. You can define the geometry and material properties. I'm just going to accept all the defaults and click Finish, and that builds a very simple problem. So we have a foundation block sitting on a block of soil. Anything I click on, its properties appear on the property editor on the right. So I've clicked on the load here, and if I expand the loading tab here, we've got a permanent load defined by the wizard. Basically, it's a normal force of 1. You can define that as a shear and a normal load, or as a horizontal and vertical. So it's a vertical load of -1, given that the y-axis acts upwards. It's sitting on a block of soil here. I can again look at its soil properties here. So the key property of relevance is the undrained shear strength of 50 here. And what we ask the software to do in this case is how much bigger does that surface load or that load on the foundation have to be to cause collapse. So to solve that, I simply press this button. Very rapidly finds the critical collapse mechanism. I can animate that just to aid understanding of what it's done. And I get a solution of 260.1. So essentially that is how much bigger that unit load of 1 has to be, and that actually corresponds pretty much to the theoretical aspect. If you're familiar with bearing capacity equation, the solution for an undrained soil should be 5.14 times the undrained strength, which in this case was 50. So that comes up pretty close to 260. The result comes up as green because we've had to increase the load to cause collapse, and we can get a summary of the results by clicking this button here. It gives an expanded detail of what we've got. So it's basically saying we have to multiply whatever load we'd specified by 260. If we look at the row here, we have a design value of effectively 1. We can put in partial factors. We'll cover that later. So multiplying the initial value by 260 gives us that collapse value. We can also look at all the other parameters in the problem. So the unit weights for soil are specified, but were not factored. And the material properties also specified, but not factored by this adequacy factor. So I'll click OK on that. So just to kind of clarify this issue with the loading, if I click on that load and I change that to 520, which is basically twice the collapse load, and click solve, I get exactly the same mechanism of failure, but now my adequacy factor is a half. That comes up in red to say it's less than 1. It's not really going to comply. And if I click on the summary, I get again this saying that it's unstable. But you can see that effectively the value that I'd entered was 520. It's been factored by this half, so I get back to the same answer that I had before, 260. And back to the same collapse value. So I can either put in unit values to ask the software what is the collapse load, or I can put in the actual expected load and get it to tell me whether I've got a factor of safety of 1 or less than 1 on that quantity. Now, one aim of the software is to allow easy interactive use and, be able to ask what-if type questions. So it might be, well, what happens if I didn't have a uniform body of soil? I had a layered body of soil, so I can split the body into 2, or even more so, I could split it diagonally like that. And I could, for example, I can take materials from this left-hand column. This is what we call the Material Explorer. It has some built-in materials. I can define my own material types. I can drag and drop, for example, a loose sand into these blocks here, and then resolve, and I'll get a very different failure mechanism driven again by those particular soil properties. So that's one way of setting things up. I can also switch materials quite easily. If I right-click on this footing soil and click switch, I can actually replace every instance of the footing soil with something else. I'll put in the soft clay here, apply that, and both of those have changed, and I can click solve and get a solution for that. Now, when I clicked solve, you'll see that it popped up with a warning that said that this boundary here, boundary B3, which is the one below the foundation, is potentially incorrect. So that's an interface material, and it's been specified to have properties that are a fraction or a multiple less than 1 of another material. So if we have a look at that, that's this particular material here. Its parent material is in fact the footing soil, but now we've changed that to the soft soil. So I need to correct that. I need to redefine that material, change the parent material now to the soft clay, which is what is under the foundation now. So I click OK, and then this button will also get me to the diagnostics, and I can see I now have no warnings. So again, in the software, these diagnostics features, it's designed to allow you to quickly get the core information about what you specified, and it flags up warnings for issues where you may have not intended what you've actually specified. So just to wrap up this kind of short section, I'm just going to click undo and revert all the changes that I've made. Hopefully you've seen that the software solves very quickly. It's now typically 2 to 3 times quicker than the previous version of the software. But if you have a very complex problem, it can take longer. So I'm going to change the nodal density here. So this is basically the level of discretization that the software uses. We'll talk a little bit about more of that in later in the presentation. Going to make it 4 times bigger. So if I click solve now, you'll see that it takes a little bit longer to solve. And obviously if I made the discretization even finer, it would take longer. So we get a solution, we get a slightly better answer. Rather than 260, we get 258. The mechanism actually this time is now asymmetrical. That's not an error for a foundation on clay. The mechanism can be symmetrical or asymmetrical. It's exactly the same collapse load. But now with this, if I wanted to save the solution, I can click File, Save, and I can save that with data. So I'll put this into folder, I'll just call it Project 2, save that. And then if I unlock, I've lost the solution, but if I reopen that and open it up, it pulls back that solution. So it allows you to save solutions and reinterrogate the solution. Particularly useful if you've set up a very complicated problem. Okay, so that's a quick look at some of the features which hopefully make it easier to use and more informative. I will just flip back to the slides. So, sorry, skip that slide. We've just done the demonstration. Just to give you a background on this discretization and how the method works. If you're not familiar with it, essentially we use a method called Discontinuity Layout Optimisation. That was developed at the University of Sheffield and first published in the Proceedings of the Royal Society in 2007. Essentially, it's a simple linear optimization problem. I'll just give a quick overview. We start off with a problem which here is just a rectangular block of soil, has a loading on the top, and supports to the left of the base. We discretize this not by splitting up into elements, but through nodes. So here we've populated it with 4 by 3 nodes or 12 nodes. And what we do is we essentially connect every node to every other node with a potential slip line. So here with 12 nodes, we've got 12 times 11 over 2, 66 possible slip lines. And then we feed that into an optimizer and it picks out the set of slip lines that give the critical collapse mechanism. In this case, 6 slip lines give the mechanism that generates the failure with the least energy dissipation. Now, of course, normally we're working with 500, 1,000, 2,000, 4,000 nodes, so effectively we're working with millions of potential slip lines, and the solver, as you've seen, can very rapidly pick out of that rich set of slip lines the critical collapse mechanism. So essentially, the more nodes you put into the problem, the more highly discretized the problem is, and the more accurate you get your result. So hopefully that gives you a little bit of background to how the software works. So now I'll move on and talk about a few of the new technical features in the software. I've listed them on the screen, but I will just crack on with illustrating them through the software itself. So firstly, we've made it easier to specify structural elements such as soil nails, sheet piles, soil reinforcement using essentially primary rather than derived parameters. So just very quickly to show that, if I bring up the new material dialog, I look at the menu here, I can create a soil nail. So here I would put in things like the diameter of the nail, the interface coefficients and so on to give that property. And for a sheet pile, for example, I'd give the bending strength of the pile a weight if I wanted to do that. I'm not going to go through those in any great detail, but what I will do is load up an example model with a sheet pile in it. So that's this one here. And just click solve. So we set this up to ask the software how much heavier does the soil on the right have to be to cause collapse. So it's setting up the problem and then rapidly finds the collapse mechanism. We could animate that if we want to see what's happening. So rotation primarily about the base. And what we've got plotted here is the bending moment in the wall. So we can plot just the structural properties there. But if I right click here, I can get a choice of what to plot. So we can now plot the pressure distribution. So I'm going to click normal stress. So that comes out like that. If I click here, sorry, both of them like that. Basically get the normal stress on both sides. Got a slider bar here which can magnify those up. So essentially on the right you can see a very narrow triangle, which is essentially the active earth pressure. On the left we've got the passive earth pressure. Because we're rotating at a point just above the base of the wall, those flip and we get passive on the right and active on the left. So that's essentially what you're seeing in that diagram. We'll now move on and just look at something more related to design codes, which is a specification of favourable and unfavourable loads. So I will pull out this model. So here we have an anchored sheet pile wall, and we've got surface loading across both the retained soil and the soil in front of the wall. Now, when you set a loading up in the software initially, it basically gives it a designation of neutral here, and that's really just a setting to say software doesn't know what you want to put in there, and it's essentially a flag to say you need to set it to be favourable or unfavourable. But rather than doing that manually or trying to decide which it is, and in some problems it's a little hard to work that out, the software can automatically let you know based on a collapse mechanism what those settings should be. So we solve the problem. We're getting a bit of a failure in the anchor if I animate that, and a bit of a failure behind the wall. But if I click here on the solution summary, and we also note there are loading type warnings, I go to this tab, it basically tells me that I've set these things to neutral, but actually some of them should be favourable, some unfavourable. So for example, if I click on this boundary B6, it highlights this one on the left. It says actually that should be favourable because that's opposing failure. But if I click this one, for example, that's a load just behind the wall, that's unfavourable, and that should have that particular setting. I can leave it at that, that's just a warning, or I can click this apply and close and it will automatically adjust all those settings for me. So if I click this load up here, for example, it now says it's unfavourable. And if I resolve the problem, I don't get any warnings anymore. I haven't actually applied any partial factors in this case, so it makes no difference to the solution. But if I had partial factors applied, then that would generally make a difference. Moving quickly on, a quick look at an enhancement to the material property definition. So where we have, for example, an undrained soil here, I click on that. In the advanced features, I can model things like an increased CU with gradient, but I can also model anisotropic properties. So in this case, I can model the vertical strength being twice that of the horizontal strength using the elliptical square function, and I have a choice of that function or a Norwegian Geotechnical Institute function or a user-defined function. So this is, again, the standard footing on a clay soil, but if I solve that and just click OK, you'll see that we get a mechanism that is quite squashed because the strength is bigger in the vertical direction. But if I flip that around, so again, I just go into here and I swap these values, so the horizontal is stronger than the vertical, then you can see that we get a much deeper mechanism. So that should allow the ability to model a number of anisotropic effects in soil, so that's particularly relevant in some parts of the world, for example, Scandinavia. Okay, we're going to just quickly flip back to the presentation, and again, I have already done the demonstration. We'll wrap up now by looking at support for design code. So obviously, many of you will be aware that we've now got the second edition of Eurocode has just been recently published. And we're going to look at a few enhancements that address that, but also extend the overall support for partial factoring and so on. So we'll bring we'll do a demonstration. We'll bring the software back up. And we'll have a look at another model. So, anchored wall. So here we have our anchored wall again. If I click on this scenario manager button, currently we've set it up for the first edition Eurocode factors DA1/2. And as you can see, primarily we're factoring material properties here, and most of the action factors are 1. And that's the same as VC3 plus M2 in the new code, essentially. So if I click OK on that and solve, I will get a failure mechanism. Again, we're asking software how much heavier does the saw behind the wall have to be to fail it. And we've got a factor less than 1. So it means with those partial factors applied, then we're basically unstable. And again, we can look at this summary table, and if I expand on the materials, they're not factored by the adequacy factor, but they are factored by the partial factor here and here. So you can see the design value is less than the representative value for tan phi. So that's using the new terminology in the second edition of the Eurocode. Okay, so we'll click OK on that and unlock the problem, and we'll go into the scenario manager again. But this time we're going to select the set VC4 plus M1. And here, essentially, we're not factoring anything, but we now have an output factoring approach. So in the Eurocode, it's basically given a bit of clarity onto how factors are applied. So we have the VC3 plus M2, which is essentially an input factoring approach, but VC4 plus M1 is an output factoring approach where we do the analysis and then we factor action effects at the end of the analysis. So we now have this output factoring option within the scenario manager. And we're going to focus on the anchor tendon in this case. So this anchor tendon here, we look at its property. It has a tensile strength of 200, but also it has, if I look at the advanced section, right, one moment, we have to change a setting. So in the preferences, we have options for the partial factors here, and I'm going to enable the output factoring option, as that's a new feature. So we go back and look at this, and we can now see that we have a structural check. So you can apply the structural check to any item you like. I'm going to set that to true. And then I will solve the problem. We can do the diagnostics, and it will find the mechanism. This time we have an adequacy factor of almost 1. So in terms of geotechnical failure, it's failure in the soil, we are okay. And that's because we haven't factored the soil properties, but we do have an OFA, output factoring warning. If I click here, click on this tab, it basically says in the engineered element or in that anchor tendon, the tensile force is 153. If I multiply that by 1.35, I get 207, and that's bigger than the specified resistance, and therefore it's flagging up a warning there. And if I right-click on the tendon, I can also, I think I've got the wrong, yeah, I can see, I need to unmagnify that, but I can basically see that the axial force is 153 by another route. Okay. That pretty much wraps up what I've got a chance to say there. I will just say that if we go to these preferences, we have the option to have consequence class factors and an extended set of partial factors. So if I now go to the scenario manager, the new Eurocode has introduced a lot more material properties that can be factored. We're also allowing factoring of other properties which aren't necessarily mentioned in the Eurocode, but that is possible if you so wish. And we have a summary tab here, which also illustrates the application of consequence class factors. So if I apply consequence class factor 3, so that's for scenarios where the consequence of failure is more extreme than for normal problems, and then all the factors get magnified up by that factor. So if I click this little box, you can see, for example, this factor here, it was 1.1. It's been factored up by another 1.1 to give 1.21. So that again should ease the application of the consequence classes, which are now as specified in Eurocode 7. Okay, I think that kind of takes me pretty close to the end of the time that I have available for that. So let's just crack on to the last few slides. So I hope showing you through that, whether you've used the software or not, that workflow is straightforward and hopefully even more straightforward than before. Very intuitive. You can solve a problem with one mouse click, and hopefully you've seen that applying partial factors is very straightforward. It's very interactive. We've sped it up so it solves even faster, so you can answer what-if type questions very quickly, get a better feel for the problem, and hopefully you've just seen you can solve any ultimate limit state problem type. So you don't need to learn how to use other programs, and we made it much easier to use reinforcement and other things like sheet piles in the software. Basically, we'll just summarize here the range of problem types that you can look at. Essentially anything that you can generate the geometry for, you can solve. So we have time for questions at this point. So we'll just have a look at the questions that are coming in. So I've got a question about global factoring. So if I just bring the software back up. So those of you that were looking at this preferences setup, there was a preference for in this drop-down box for global factoring. So if I click global there, essentially that just goes back to sort of conventional, traditional way of doing geotechnics. So I click on the scenario manager. It's much, much simpler. Basically, you can flip between short and long-term analysis, but that's true for any of the setups. When you have a target adequacy factor, here it's set as 1. If you were solving, looking at the, say, bearing capacity of a foundation, the traditional approach was to put a global factor of 3 on that. So we could set that to, for example, 3. The software would simply flag up whether we've complied with that or not. So that's essentially the global factoring approach. Another question was about slipline thickness, so maybe that's easiest to show on a simple footing. So if we resolve that again, those of you that used the software before will notice that we've now got thicker slip lines here in the unanimated mode, and that essentially is showing you the thicker the line, the bigger the displacement. So if I animate that, those thick lines you will hopefully see are actually undergoing greater displacement than the thinner lines. So that's another feature that hopefully will aid interpretation of the results. And then I have one more question on triangular loads. So will we be able to specify triangular loads? So in this current demonstration, the loads are basically uniform loads. So it's a very good question. We will have a look at that and see when that's something we can squeeze into the next release. So that would be the ability to vary loads in a triangular or in a trapezoidal mode across a block, to save having to break it into individual sections. Okay, I think that pretty well wraps up what I want to say. So it just remains me to say, as we're so close to Christmas, have a great Christmas and a good holiday break, and I'll just pass back to Tom to wrap up.
Thank you, Colin, and thank you all for joining us today. We do hope that you've enjoyed exploring the new features and capabilities in LimitState GEO version 4. There's definitely plenty to try out, and we're very excited for you to put it into practice. If you have any questions as a result of the webinar or just in general, then don't hesitate to reach out to us at info@limitState.com, and we're always happy to help and answer your questions. If you'd like to watch the webinar again, or perhaps share it with your colleagues who want to see what's new, a recording will be made available in the next day or so on our YouTube channel, which is LimitState Software, and we'll email a link once it's live and post it on our LinkedIn page as well. Looking ahead, our next series of webinars will take place in 2026, where we'll be diving deeper into LimitState GEO version 4 and its applications across different problem types, as well as our other software titles. So do keep an eye on your emails, our website, and on LinkedIn as well for announcements. Lastly, just thank you again to everybody for joining us today, and we do look forward to welcoming you back in 2026 for even more insights into the latest capabilities of LimitState GEO. And like Colin says, have a very good Christmas and holiday break, and we'll see you all in the new year. Goodbye.